Welcome back to the PLC Professor's Workshop. This is part 2 of our discussion on the assembly machine number 1. That means we'll probably have another project that we'll do later. That would be assembly machine number 2. This is machine number 1, and this is part 2 of machine number 1. I recorded part 1 yesterday, and I decided today that I had some time, so I'm going to jump in while it's still fresh and do part 2. In part 1, we did kind of the lineup, discussed all of the hardware components, why they were picked, how they were picked, etc. Now we're going to start talking about the electrical design. And my advice for the day is make sure that you're putting your spiritual condition first, then your physical condition, and then your intellectual. What we're doing is intellectual. So I hope you put your spiritual first, then your physical. By spiritual, it's whatever that makes you feel good spiritually. And then physically is exercise and eating decent. There are parts of your body, organs, that I won't go into detail, won't work correctly unless you have motion. Literally, glandular systems that get rid of toxins out of your body, poisons, but they don't circulate by themselves. You have to flex your muscles in order to get them to expulse the toxins. And once they're full, they don't collect anymore. So then you just stay kind of feeling a little sickly. So if you put the spiritual first, the physical will be easier to do, the exercise and the eating right. And if you put spiritual and physical, then your intellectual activities will be probably 10 times more effective. You'll get so much more done in the same period of time. Now I'm saying this to remind myself. I need reminding all the time because I just want to jump out here and do my work, both the design on the project and these recordings, and worry about the physical and spiritual later. But I'm forcing myself, spiritual, physical, intellectual. So let's jump in and design. Okay, this is the second time I've done this. When you're recording with software and cameras and microphones, you can record your screen and the camera and the microphone. I tend to do either the screen or the camera, not both. So what I'm going to do right now, I'm doing over because I did it once, but I had the camera on, and all you see is the light from the screen on my face and me waving my arms around. So let's jump in here. Very first thing I do on electrical design, that's once I've cataloged all my components, meaning I have a sheet or I know by heart the part numbers and the details of every single component that I'm going to use in the design. So you always start with power first because that's the first thing that in a way comes into the panel. All manufacturing facilities have three-phase power. Now there's a possibility that one has the same part comes into your garage or your breaker box that's two-phase 220. So you have two phases, two circuits between the two hots and neutral give you 120 and 120, or you can use them together for 208, but we're not going to use that. But that's what two-phase 208 is. In this case, we're talking 243 phase. Now, if you don't know what three-phase is, here's a quickie. What comes into your house to your outlets, not to the breaker box, it's got two-phase. But what comes to the outlets in the wall is single-phase, 115, 120 volts AC, alternating current. What that means is that the current flow, the electron flow in the copper conductors flows in one direction and then in the other direction, reversing 120 times per second. So for half of the 60 cycle, 1/60th of a second, so for 120th of a second, current's going one way in the wire, so it goes from 0 up to maximum, drops back down, reverses, and goes the opposite direction for 120th of a second, back down to 0, and then repeats that cycle. Alternating current, 60 cycle. So if you're running a motor, every 1/60th of a second, you get 2 pulses of power to that motor. Now, the motor doesn't go back and forth in direction because there are either brushes, commutator segments, electronics that always push the current the same way through the motor if the motor requires current to stay in one direction to control its direction. Now, there are induction motors that don't, because when the phases or the direction shifts in the stator, it also shifts in the rotor. So they're always pushing. It always pushes it in one direction. With a standard AC motor, single phase, you get 2 pulses of power every cycle, or 120 torque pulses per second. With 3 phase, you get 3 times that, because you have 3 single phases 120 degrees out of phase with each other. So when one's increasing, another's decreasing, etc. So you get much smoother power from 3 phase than you get from 2 phase if you're feeding a motor. So that's the reason for 3 phase. That's why all manufacturing facilities use 3 phase. It's more efficient. In other words, you're getting more power. I guess you could say you got a better duty cycle on your conductors. It's just a bunch of reasons. And the reason that they use high voltage is because the higher the voltage, the lower the current. Volt amps, volt amperes, power, watts, volts times amp. 480 at 1 amp is 480 watts. 120 at 4 amps is 480 watts. But it takes more copper to conduct 4 amps than it does 1 amp. Now I'm using just some real simple numbers. That's why they use high tension lines, because the higher the voltage, the lower the current to get the same power. So you can use smaller conductors, less expensive. Okay, 3 phase. Now in our system here, we've only got 1 3-phase load. That 1 3-phase load is the variable frequency drive. You'll see that I have 3 conductors coming through fuses to that variable frequency drive. Now, I always start in the upper left-hand corner and I bring in my 3-phase power, because remember, that 3-phase power drops from the ceiling, from the bus and the plant, down to your panel. Comes through an opening, and the first place it goes is the disconnect. Goes to the top terminals on your fusible disconnect or your circuit breaker. Circuit breakers have a little toggle switch on them, and if you're using this for a disconnect, then that means that you have a mechanical device on the door that you can turn this circuit breaker off from outside with the door closed. Or if you're using a fusible disconnect, you've got a mechanical mechanism, and there's 2 types: through the door or flange mount. The flange mount, part of it mounts to the enclosure and the other part mounts to the back panel, the back plate. Whereas a through the door, you mount the fusible disconnect on the panel, and then it's got a square rod that sticks out far enough that it'll go through the door when the door is closed. Cut a hole through the door, mount the handle on it, you know, the rotating, what you might call the switch handle, and there you go. I prefer flange mount, but they're more expensive. The advantage of a flange mount is they're easier to operate than wrestling with those through the door disconnects. Either one works. All it does is interrupt power from outside the panel with the door closed. And they all have some sort of thermal circuit interrupters, whether it's a circuit breaker or fuses. I'm using a fused disconnect, and it's probably a 30 amp rating, 300 volt 30 amp. They're rated by voltage and by current. Others are 600 volts. So if you've got 480 coming in, you need a 600 volt rating on your anything that's got 480 volts on it. You need a 600 volt rating. And then with disconnects and fuse blocks, it also, besides 600 or 300 volt rating, it's also got a current rating, the maximum amps you can run through each pole. So a 60 amp rating is a larger device than a 30 amp rating. If you have 240 volts, 3-phase for your design, there's no reason to spend the money for a 600 volt rating device that takes up more space and is more expensive. Okay, so in we come with 3-phase in the upper left-hand corner. We immediately go through the fuse disconnect. You can run your 3-phase like I did in vertical strips along the line numbers. You see I have 0200 through 0239 and so forth. Or you can run them across the top horizontally and then drop your loads down from those 3 wires. I choose to put my three-phase vertical and then come off horizontally with my loads. So I've only got one three-phase load, and that's that variable frequency drive. Now remember that the fuses are there to interrupt the circuit to protect the wiring, not the load. So the fuses in that main disconnect are there to interrupt the current if the wires going from that disconnect to all of the fuse blocks, if it exceeds the rating. Now, coming off of the three-phase going to the variable frequency drive, I have another three fuses. Those are there to protect the wire going to the drive and to the motor. In my case, that drive is in the panel. So I'm not really protecting those wires as much as the wires going from the drive to the motor. Now, why do we do that? Because if you melt the insulation on the conductors because of an overcurrent and it's inside conduit, you got a mess, and you're going to have some real unhappy people in corporate, because you're going to have to shut the whole thing down, probably rip out the conduit. Sometimes you can pull out the melted conductors, sometimes you can't. So the circuit interrupters are there to protect the wire. If you need some sort of specific fusing sensitive to the load, then you need to add that to the load, right at the load. In this case, these fuses are sized to protect the wire, not the load. But why not specify fuse sizes? By sizes, I mean current rating. That is something like 125 to 130% of the maximum current for the device. It'll protect the wire and give you a little jump in protecting the load. Because you can overdraw current not below the fuses that protect the wire and still burn up your device, because they're there to protect the wire, not the device. Okay, enough said. One three-phase load, the VFD, and now we've got three controllers for the robots, R1, 2, and 3, and we're supplying them basically with 208 or 240, in this case 240. And that's two phases of this power. So notice that we're not running a third phase to these three squares that represent the power connection for the robot. Now that's not the whole robot connection, that's just the power. The interface to the robot from the PLC, that's on another page. Okay, so all we have drawn here is a box that represents the controller for three robots, and it shows power going through fuses. Then we have the epoxy dispense system, fluid research power, that is a pre-built, already functioning, commissioned two-part mixing system that you program what size shot you want, you put in a request, it pumps out that size, and then it stops. So it's a completely separate machine with its own PLC. And the reason that I'm running power to that epoxy dispense is because the epoxy dispense sits right by the cell. It has an e-stop on it, and if we hit the e-stop on the main machine, you know, the main panel, we want the fluid research to stop as well. And if we hit the one on the fluid research, we want the main one to stop as well. So as long as we're doing that, we're running the power through the disconnect and the main panel to the panel that came with the epoxy dispense. And of course we have two fuses to do that. The last device on this page is the power supply, 24 volt DC power supply. There's actually two devices there. The first one is the transformer. So we got two fuses feeding the primary of the transformer. Now a transformer transforms one voltage level to another voltage level. In this case it's a step down. I'm stepping down from 240 down to 115 or 120. Now I don't show it, but the actual transformer has more than 4 terminals. So it allows you to make the proper connections for primary and secondary for the ratio that you want. Voltage in, voltage out, etc. And this particular transformer has fuses mounted right on the transformer. There's an advantage to that because it saves panel space. And believe me, this transformer is bigger than that power supply. A lot bigger. Because you've got a lot of power going through it, and you've got the fuses mounted on it. Then we've got a power supply, 24 volt DC. I don't remember the amperage. I was thinking it was 8 amps or 10, 12 amps. I don't remember. So the only conductors leaving this page, going to another page, are the ones that have references. And that would be these two right here that are the 24 volts DC. That's 24 volts DC and that's 0 volts. They're going to another sheet, sheet 4 actually. You can't read the references, but it's going to sheet 4, and that's where we pick up the 24 volts DC. There's no AC leaving this sheet. If there were, then these 3 conductors right here, or 2 of them at least, would drop on down and have arrows down here like we do over here. So this reference right here references this arrow up here and so forth. So we transfer our 3-phase over to here, and then it stops here. No AC leaving this sheet. So now let's jump over to this sheet, sheet 4. That's the control. And here's our control sheet. It's all 24 volts DC. If you were to go back to the power sheet and look at this reference right there, you would see that it is going to that reference right up here at the top in the upper left-hand corner. And the other wire right here, it's referencing this line number right here, which is really the same line number, 0400. Okay, so this is 24 volts DC and that's 0 volts DC. This reference down here from this arrow is linked to that wire, and this one is linked to that wire. And then down at the bottom here, this one is linked to the top wire on the left corner in the next sheet, and so forth and so forth. You'll see that all the way through the drawing set. And you can do that using links. So if I click one of these, up in the menu I show a link. Now the fact that I have a link with an X means that it's already linked. But if I didn't have it linked, I could click there, click on that button, and then go to here and click, and the automation in the software package, the CAD package, automatically considers that the same conductor. And that's very important for the electricians and the panel builders. Okay, so let's take this first device. So I'm going to zoom in on this. This is the epoxy dispense. Remember that this epoxy dispense is its own complete separate system that will work without our PLC, without our panel. But we don't want it to. We want to control it with external signals. One of the external signals is e-stop. If we hit an e-stop on our panel, the main panel, or anywhere in our work cell, we want the epoxy dispense to go into e-stop as well. To do that, this epoxy system has 4 terminals that we can interface 2 channels of our safety programmable relay into its safety circuit. So these would have jumpers across them. So you would have this terminal jumper to this one, and then this terminal jumper to that one if you had no external e-stop stuff. Okay? So you could say this is where you would hook an external e-stop, 2 channels. This is a single connection going back to the main panel safety circuit. Now, this isn't totally built into this epoxy dispense system. So when I commission this, I'm going to have to go in and actually do a little hand work with wiring to make these 2 terminals suffice as a signal from this e-stop safety going back to the main panel. So this is channel 1 and channel 2 from the main safety relay in the epoxy dispense system. I'm using those 2 channels in series to send a signal back to my safety circuit, which we'll get there eventually, and this is in the safety sheet. And see, here's the epoxy e-stop right here. Okay, so this is our main safety relay. So I want to get too far out of what I'm doing here. We'll do the safety later. Okay, so here we got external e-stop coming in, internal e-stop going out. That connects the 2 systems together, e-stop, 2 directions. Here we've got inputs, and here we've got outputs. So here's where we tell this thing to dispense or not to dispense. And here's where it tells us it's ready or it did the dispense as we requested. These are discrete I/O. This, as I told you, this LC30 does not have Ethernet. Otherwise, I would be using Ethernet, not discrete I/O. But this is fine. This works good. Now this signal right here, the reason it's red and has a question mark, I haven't decided what to do with it yet. This system tells my PLC, this PLC tells my PLC that it's ready to dispense. Then my PLC tells this PLC, dispense. And then this PLC says, okay, we dispense, we're done. Or if from my PLC I decide to cancel it, this cancels the dispense. This is a heartbeat signal, and there's a variety of ways that you can program that. And if that's not high, then the epoxy dispense is going to ignore a dispense or a cancel. So that's like a heartbeat from another system, a main system, to this. Okay, that's the epoxy dispense. And I showed as a dashed line because it's not in this panel. Right below it, we have, notice it says EX600. This is the power and Ethernet connections for the SMC valve manifold assembly. Remember, we're using an SMC assembly that has solenoid valves on it. It also has two multiple input modules, discrete input modules, and one output module. So that's remote I/O. This is the power for that assembly. So this box right here, that's all it represents, is the Ethernet connection and the power connections. And then over here we have our two stepper motors, the AMC SMD 23E and 34E. And what I did is I put the details down at the bottom for the connectors. So these are just square blocks that I made and threw terminals on them. I can see now that I did not go and edit the terminal numbers that automatically populate when you create one of these in the CAD package. So these pin numbers don't match the pin numbers on these details. I'll go back and change those. But they don't have to be there because remember, these are connectors. You're not actually lining wires on what like screw terminals here. This is a plug-in connector, so that connector can only go in one way. You cannot hook the wrong wire to the wrong wire when you're using these cables and connectors. This is the 23E and this is the 34E. Notice it has three connectors. It's got two Ethernet and a power I/O. Here's an Ethernet and there's a power I/O. And then this one has a separate power and separate I/O and two Ethernet connectors. One thing I want you to notice on these power connectors is notice it has, you can't read that, but it says DC power aux, DC power main. So one of those, if you leave it applied, controls only the electronics and not the motion of the motor. This one right here, the main, if you remove that power, the stepper motor comes to a screeching halt right now. But if you leave this power there, 24 volts DC, it doesn't lose its mind. It knows where it's at, knows what it was doing. You just basically told it to stop. So notice that I'm using two channels from K1 and K2 in the main safety circuit to interrupt power to the stepper motor, and I'm doing the same thing down here. These two lines right here are the two inputs to the steppers. Actually, I think this one has three. You see, if you look down here, input 1 and 2 common, input 3 and input 2. So I don't know why this one doesn't show a common, but anyway, it's got three inputs and a common. So the 23E and the 34E have slightly different physical characteristics, but the Ethernet's the same, just this has separate power and this has separate I/O. Notice that these Ethernets are daisy chained. That's why there's two Ethernet connections on each of these. So I can come in with an Ethernet cable from my Ethernet switch that's in the main panel, because this stepper motor is not in the panel. It's on the machine. It's on the fixture, the table. And then I can use another cable to come out of this Ethernet and go to this Ethernet connection, right there, this one. And I could jumper from this one, which I probably do, and go over to here. So I'm daisy chaining And the whole idea of a lot of what I did here is to reduce the challenges of commissioning a machine in one state, tearing it down, shipping it to another state, and reassembling it and recommissioning it. So the more connectors you use, cables with connectors that are properly marked, the less fooling around you have to do in junction boxes, especially when you have wires that the numbers have fallen off to, or maybe they didn't mark them at all. So what we have here is, this is a cable. These 4 wires right here are a cable that goes from these cables to these cables. So you actually have, well, this is a connector. These connectors right here are the ones on the stepper motors. And then those cables go to another cable that has flying leads on it that actually land on terminals in the PLC panel. That's about all I can squeeze out of this for right now. So let's go to our controller, our Compact Logix. Now, you don't see anything here that looks like a Compact Logix. There's a reason for that. And that is this CAD package, you create your own blocks. So, and this one right here is not entirely finished. I can see that the lines are in the wrong position. Doesn't affect anything. And I've got an extra Ethernet port. So this PLC has 2 Ethernet ports. It's an ER, L27 ERM, ER for Ethernet redundant. And so I'm coming into one port and going out the other to something else, but notice I don't have the reference there yet. I do have a fuse for the 24 volts DC to this PLC, PAC. Okay, this is an input module to this PLC, but it's all embedded in the plastic. So an L27 ERM has 16 in, 16 out, and then it has 4 analog in, 2 analog out, then high-speed counter terminals. They are embedded in the controller. And here I'm showing them as separate boxes. That's just the way you have to draw it. So this is my 16 inputs, discrete inputs. I've got 3 from guard door switches, and then remember our epoxy dispense right here, our outputs? Those go to inputs here. Now I'm showing 4, but remember I didn't have 4 outputs from the epoxy dispense to the controller, the input module. But I'm showing 4 connections because I want it wired up that way. So if I want to add something from epoxy dispense into this controller, the wire's already there. I just have to program it. Now the guard door switches, these are not safety inputs. The guard door switches each have 2 channels that go to the CR30 programmable safety relay. These are aux contacts, auxiliary contacts, that you can use to see that a guard door is closed or not closed, and you can use that for your HMI display. Now you could have done the same thing through Ethernet, because our CR30, we're using Ethernet, so I could have accessed some of that information and figured out a way to do it on the HMI anyway. But hey, if the guard door switches have aux contacts, let's use them. The more the merrier. Okay, we're in local I/O right now, and I have 2 sheets. This one, and then I have another one that has the digital output and the analog input output. So, from my digital out, I have 2 discrete to each of the steppers. I'm not using them for anything initially because I'm doing it with Ethernet. And I'll talk about that much later, how you can do it through Ethernet. You don't need discrete. But I'm hooking them up. Guess what? If I decide I want to use one, I don't want to go find somebody that's authorized to add conductors into my panel. And remember, these run out to the stepper motor, another added complication. So you got a pre-wired in advance, and then these 4 go through a conduit to the epoxy dispenser. Remember, we've got request. I can't remember what the 4 are. We'll jump back here. So we've got ready to dispense. Oh, wait, we're going out. Dispense request, master control healthy, cancel dispense, and return request. That's what these 4R right here. This is our analog input and output. There are 4 inputs and 2 outputs. Why all these screw terminals? Well, you got voltage plus, current minus, and common. So you might have up to 4 conductors for each. In this case, I think it's 3. So 1, 2, 3, 4, and then you got some commons or something. Anyway, there's a reason why I put all these screw terminals on the analog input-output module. But I'm only using one analog input. This is a level sensor. So it's basically an ultrasound. And it looks at the level of the epoxy being dispensed into the chamber where the electronics is in the nest on the assembly machine. So the dispense system is set up to deliver a specific shot of 2 parts mixed into one to pot or epoxy the electronics. So this just monitors the result, verifies that it is the level it was supposed to be, or overshot or undershot. So that's the only analog on this whole machine. One analog input. Okay, Ethernet. This is a 16-port switch, industrial switch. It's not managed. We don't have enough Ethernet activity to require a managed switch. Better than a hub, though. And if you're new to this thing, an Ethernet hub is, I was going to try to make it a hub of a wheel, but let's just say that with an Ethernet hub, and remember, Ethernet is only one node, one location can be putting information on Ethernet at any given time, okay? So a hub, if a packet comes in on any one of these 16 ports, it goes out the other 15, period. So at any given instant, you got an IP packet coming in 1 and going out 15. With the switch, it's a little bit more efficient in that if you've got something coming in port 1 and going out port 5, it leaves the others somewhat open for other activity. A managed switch goes one step higher and basically pre-configures routes through that. So anyway, this is just an Ethernet switch, a standard, inexpensive industrial Ethernet switch. Notice I don't have all of these Ethernet cables referenced yet, and of course we have a fuse to protect it. And our Ethernet diagram might eventually show an HMI or something. Right now it doesn't. We've got the HMI on another sheet showing an Ethernet connection, but no reference back to the hub. And we could do that right now, but I'm not going to. I don't want to waste your time making you watch it because you may not be using this CAD package. And just let me reiterate, if you're not using a CAD package, you need to. You need to learn one now. Start now. This is a good spot to start. Go get SkyCAD. You can use it free. A lot of the automation works with the free version, but you can do the basic drawings and then later on decide if you want to subscribe. AutoCAD's cool, but it's expensive. Let's go to remote I/O now. Okay, with remote I/O, we've got an Ethernet connection. You can see it right up at the top, and you can see it's daisy chained. We got Ethernet coming in and Ethernet going out. Then there's electronics in here that gather up the state of all 16 of these inputs. Notice there's 8 connectors, and each connector has a T or Y or splitter on it. And you can connect up 2 sensors, 2 inputs to each input port. And so if you look at the detail down here at the bottom, here's your 4 pins going into the armor block, and here's your 6 terminals, one from the one sensor and one from the other, because they share common and power. So if you look close here, I've got 24 volts going here and going here. This is 0 volts. And I don't show a conductor going over here, it's just implied. And you can do this with a field wireable connector, because this 4 is the 4 that has to screw in, plug into this block. But these 6 can actually be done with 4. This is your input right there. That's the input for that sensor. That's the input for that sensor. That's 2 wires. This wire and this wire both are 24 volts DC. So you can take this wire and this wire and put it inside of one screw terminal inside that field wireable connector. And then you can do the same thing with the commons. Okay, so this is remote I/O. These are inputs only. And by the way, I know that looks like a limit switch, but that is technically a solid state sensor. This software didn't have a symbol for a proc switch that had a diamond around it like you typically see, but it does the same thing. So I could have gone and created another symbol. I didn't. I just used these. So keep in mind that these are solid state sensors, all of them. And I will use up these 4 spots right here before I'm done. So I can have 4 more inputs here. And notice that the connectors, they are automated. In other words, see, this one says connector 1, connector 2, connector 3, connector 6, 7, 8, 9. So this automates that whole process. Now you do have to, you create a connector in the database, and then you click on this and say this belongs to connector 1. That's why you see the pin numbers. That's pin 1 and that's pin 2. Well, that's irrelevant because remember, this is one solid physical device that screws into this armor block, and then these are probably cables, 3-wire cables that plug into these 2 connectors. Okay, so that's remote I/O. So I think we're going to leave it right here for right now. Sufficient to the day is the evil thereof, so to speak. And the first one was, I don't know, 55 minutes. I know that's too long, but as I said several things. One is, this is not entertainment. If you're looking for entertainment and you're not, absorbed into the knowledge transfer, stop the video and go to something else. Don't waste your time, and then don't send me something saying how boring it was when you could have just turned it off and went to something else, or fast forward. Now, if I'm showing a talking head, you can't tell what I'm talking about if you move the progress bar along. But when I'm looking at the screen like this, you can see what's on the screen. So you can move it along and then back up to where that image starts and continue from there. So we're going to leave this right here right now, and we will pick this back up with the robot interfaces for the end-of-arm tooling. This is wiring that takes place from the end-of-arm tooling, the grippers and sensors, to the robot itself, and has nothing to do with our PLC. Now later on we'll talk about code of how you can transfer that information back out to your PLC and the HMI so you can display it. But that wiring all takes place totally within each individual robot. Then we've got the controller interfaces. That was probably the most involved of the whole project, was doing the controller interface to each robot. And then a little more for the VFD. Then we've got the I/O modules for the SMC valve assembly, and then cables and connectors, panel layout and terminals. So we'll see you the next time. Thank you for listening. Have a good day.